welcome back, everybody. Now we are ready for dark matter number 2. Hope you all enjoyed that first video. I'm gonna try to do better with every one. So here we go. Dark matter. We talked about those rotation curves, and now we need to talk about what is this weird stuff that's causing those flat rotation curves. Well, we know from the flat rotation curves that this stuff has to mostly be located in the outer parts of the galaxy. Okay? In the outer parts of a galaxy, and in fact beyond what we can see of the galaxy itself. So the outer parts of the galaxy and beyond, in what we call a dark matter halo. So the halo is, as you can see in the picture here, this big area around what we can see. The red part is just that spiral galaxy, but we think that there is matter, dark matter, way out, causing these flat rotation curves that go way beyond what we can actually see. Now, we've been talking about spiral galaxies with the rotation curves, but once we, as astronomers, learned about dark matter, we started to think of ways to look for dark matter around elliptical galaxies as well. It turns out we see it there too, that dark matter dominates ellipticals as well. Sorry about those eyes, having trouble with those. Dark matter dominates elliptical galaxies too. But we don't find it by rotation curves. Instead, we look for it by looking for gas, specifically hot gas. We use hot gas to trace where there is mass, to trace the mass. So how does that work? Well, hot gas is very light. It moves around, it escapes very easily. If there's no gravity to hold it in, then it's going to go. It's going to go away into space. So what we do is we look at an elliptical galaxy. Here's one right here, what we could see with our eyes and optical. And then we look at it in X-ray, in hot gas, and this is what we see. We see there's hot gas way out here in the halo. We can't see stars out there. It's not luminous matter. It's dark matter that's holding that gas in. If there weren't matter there, if there wasn't gravity there, then that gas could not be there either. So we look at these galaxies, the spirals and ellipticals, and we find that most of the mass in these galaxies is dark matter. About 90%. This is crazy, folks. About 90% of the mass of a galaxy, that's an of a galaxy, is dark matter. In other words, these halos are huge compared to just the galaxy itself. They extend so far out into space, they hold so much matter that we think that it's mostly dark matter. Okay? Alright, I'm going to try to write more neatly. It's tough, guys. So, 90% of the mass of a galaxy can't see it, doesn't emit light. What in the world could it be? That is the big question, and I won't have a perfect answer for you. But I do want to talk about two possibilities. Okay, two proposed types of dark matter. And I'm going to abbreviate so you don't have to look at my messy handwriting too much. These have great names, makes them easy to remember, if you can remember the names at least. The first is a macho. Machos are short for massive, because we need mass, right? Compact, because if they're small, they're hard to see. Halo, they have to be way, way out there. Objects. Okay? Massive, compact, halo, objects. What could these be? Well, these are things that we've actually already talked about. These could be things that don't emit much light. Maybe they emit some light, but they're hard for us to see. These could be things like white dwarfs. Okay, they're very, very small, even though they emit light. They're small, so they're hard to see. Other things that are small and hard to see, neutron stars and black holes. We do have ways to detect these, but we could imagine that there might be a bunch of these that we aren't detecting. So that's one idea. Okay, the second idea, and we'll come back to that just briefly to talk about how we look for them. The second proposed type of dark matter, to go with those machos, are WIMPs. All right, and WIMPs stands for weakly interacting, meaning that we don't see them because they don't interact with matter very much. They are weakly interacting, but massive, right? We got to have mass, 90% of the galaxy, massive particles. These guys aren't big objects, but they are small things. Weakly interacting massive particles. These are theoretical things with weird names like ferminos and neutralinos. They are like neutrinos. We've talked about neutrinos that come out of stars from fusion that pass right through us every day and we don't even notice. These would be like that, but they'd have to have more mass. Neutrinos don't have enough mass. So these have to be really heavy particles, but really hard to detect. Okay, so those are WIMPs. So how do we look for these guys? With the machos, we use relativity and this idea of gravitational lensing. Okay, gravitational lensing actually lets us look for those dark places, those black holes and things that are hard for us to see. Lets us look for machos. Lets us look for machos, but we don't see them. Okay, we found a few, but we don't see 90% of the galaxy's mass worth. We don't see enough mass. Okay? And so this picture over here just gives you a sense of how this would work. You have a distant star over here. Then you have an object, your black hole, your white dwarf, moves in front of it, and it changes the path of the light. It bends the light. Remember, gravitational lensing is when light is bent by gravity. So you have something that's small and massive in between you and a star. The light gets bent. So it would appear to you that that light gets magnified, it lenses, it gets brighter, and then goes away. Found a few this way? Not nearly enough. There'd have to be a ton of them out there. So what about those WIMPs? Well, this is an interesting photo here of a piece of equipment. We actually look for WIMPs in the laboratory here on Earth. We do physics experiments So experiments here on Earth, search for WIMPs, because we should be able to somehow see some evidence of these guys, even if they're weakly interacting. Maybe we could design an experiment to see them, but we haven't found them yet. So that's the but. Haven't found anything that fits the bill yet. We have a few candidates. People get excited occasionally about a particular particle, Higgs boson, things like that, but nothing that explains all the observations that we see. There is one other idea here, and that is maybe it's not a macho or a WIMP, but maybe our physics is wrong. So I'm just going to throw that one in there too as food for thought. Alternately to the machos and the WIMPs, we may need to change our physics. There might be something that we are not understanding. Just like when Einstein came along and revolutionized things with relativity. Maybe there is something else on the horizon. And there are ideas, of course, but hard to tell. Okay, guys, so that is video number 2 on dark matter. Here's your last clicker question. Take a look at that and go on Moodle and answer those clicker questions. There are a couple more videos there for your information to watch on what is dark matter, some interesting ideas having to do with parallel universes and such. So enjoy those.